Okay, good afternoon. Welcome to Chapter 4. Maybe you'll recall that the name of the course and the name of the book is Structure and Interpretation of Computer Programs. And we've done the structure part, and now we're starting on the interpretation part. So what does a computer program look like, and what does it mean? And now we're looking at how is a computer program understood by the computer. First, the administrative stuff. I understand there's a midterm 2 days from now. It will be the same place the other ones were. There's a group part that comes first, and then the individual part. Question 0, same as the last 2 times. Hope everybody gets it this time. And you're allowed 3 pages of notes, sort of 1 page per chapter to edit on. And if somebody left a YWCA Shadow Day t-shirt here, it's over there. And Saturday is Cal Day. For those of you who haven't experienced Cal Day before, people from all over come to visit, and we have a bazillion different events for them. And one of the events that we have is a Scratch Lab for kids, and we'd love to have volunteers to help run it. I guess especially those of you who are CS10 alumni and therefore know Scratch. But it's not hard to learn Scratch if you understand Scheme. So you can volunteer anyway. Okay. So the big topic this week is the Metacircular Evaluator. That's a big name, which I'm not sure I understand even yet. I understand the circular part because, well, no. There's 2 kinds of circularity involved. Maybe that's why it's called metacircular. One kind of circularity is a mutual recursion, which you've seen before in the calculator program and the Scheme 1 interpreter, which is the mutual recursion between eval and apply. So that's one kind of circularity. And the other kind of circularity is that it's a Scheme interpreter written in Scheme. We could use a different programming language, write an interpreter for Python or something. But there's 2 reasons why Scheme in Scheme is a good choice. One of them is Scheme is the only language that we're sure you all know. And the second one is, as you'll see, Scheme is a really, really easy language to write an interpreter for. It's probably the easiest one there is. So there's this picture on the board here, which I may have shown you, I don't remember, when we were talking about Scheme 1. But on the left, we have a function machine. So it has an input hopper and an output chute, and it's the function x maps to 3x plus 7, and I put a 5 in at the top, and I turn the crank, and out comes 22, just like you learned about in middle school, probably. And what's on the right is something really different from that. It's a machine that has 2 inputs. The right input is data, just like in the first machine. But the left input is program. So it takes a machine as input. And this machine is a universal calculator. It can calculate. This one on the left calculates a particular function. The one on the right calculates any function because you find a way to encode the function you want in a form that we can present to a computer. In our case, that's a Scheme program. So we would write lambda of x plus times 3x 7. And that's an encoding of this machine, which we can use as an input to this machine that, following the textbook, I've represented using a yin-yang symbol. Yin and yang are a mutual recursion. That's why there's a little dot of yin in the yang half and a little dot of yang in the yin half. And that is supposed to remind you of the mutual recursion between eval and apply. And this machine is a universal machine. And let me remind you that this idea of universality is the thing that made the modern computer revolution possible. That long, long ago, we had machines that could compute particular functions. Okay, so back in the days of Archimedes, they had very complicated machines full of gears and things, and you would turn a crank and see all the planets rotating. But it's not until the 20th century that we had a universal calculator, despite certain sort of false starts like Babbage's famous machine that was a kind of universal calculator, but he never got it built, basically because he didn't have electronics and it's too hard to do mechanically. But today we have universal machines, and that's what makes it possible for people to build new computer applications really easily. You know, you can sit in your back room and program up a new invention. So it's a really, really important idea. And that's why it's important why you understand this notion of interpreting a program. And of course, there are lots of levels of understanding of that. When you get to 61C, you'll learn how the actual hardware carries out the tiny little instructions step by step that make this all possible. But what we're doing is, at a higher level of abstraction, understanding how you can write a program that understands computer programs. Okay. Up on the screen is a little one-screen-full scheme interpreter. And this is the whole thing except for a few sub-procedures. And the few sub-procedures take up, you know, the first half of chapter 4. And to understand this, you look at the little binary tree over there representing the 4 kinds of expressions that exist in scheme. And again, this is typical of any programming language, really. So the first kind is something that's self-evaluating. The canonical example is numbers, but also number sign T and number sign F are self-evaluating. And there are a few more things, more obscure ones that we haven't really looked at. The next kind, the other kind of atomic expression, atomic is just the opposite of list, something that isn't a list. The other kind of atomic expression is symbols. A symbol is something like hello, or X, or pi. And symbols are the names of variables. And so we evaluate them by finding out the value of the variable. And then there's 2 kinds of list expressions. And which kind it is depends on the car of the list. So if the car of the list is a keyword, that is to say it's one of the words define, lambda, set bang, if, cond, what did I miss? Define class, I guess, if you load the object system in. And or, thank you. Those are the keywords that name special forms, and there's fewer than a dozen of them. And again, every programming language has something like this, special syntactic forms. They usually don't look so much like procedure calls. You can see that, you know, they have braces in them and things like that. And in Scheme, a list that is not a special form is a procedure call. The difference between a procedure call and a special form, for our purposes, the basic difference is procedure calls are evaluated using applicative order, which means what? Hands up. Who can tell me what applicative order means? Yes? The arguments are evaluated first, yes. So we start by evaluating all the sub-expressions, all the elements of the list, and then we actually call the procedure with the argument values as its arguments. A special form is essentially normal order. The special form gets to see not the values of sub-expressions, but actually what you typed, the sub-expressions themselves that you typed in. And the special form gets to decide which ones it's going to evaluate in which order, and so on. And that's it. That's the language. Okay, so as in the two previous evaluators, starting with the calculator one, there are three main procedures here. There's the read eval print loop, which says print the prompt, read an expression from the keyboard or whatever, from a file maybe, and then eval that expression. And in scheme 1, it just said eval read. But now with the environment model, we know that you have to evaluate an expression in a particular environment. And for the ones you type in at the scheme prompt, it's the global environment, always. So we eval whatever you type in the global environment, print the result of that, and then loop. So read, eval, print, loop, REPL. Eval, the structure of eval is a cond because there are 4 kinds of expressions. So eval takes 2 arguments, an expression, exp, and an environment, env. We don't know yet what an environment looks like. If the expression is self-evaluating, then we don't even look at the environment. The value of 3 is always the same no matter what environment we're in. So we just return exp. If exp is a symbol, then we look it up in the current environment. So this is where you have to understand what you learned at the beginning of chapter 3 in the environment model, that an environment is a sequence of frames. So the current environment consists of the current frame, the one we just created for this procedure call, and that frame points to another frame, points to another frame, and eventually at the end you have the global environment. Everything indirectly points to the global environment, which doesn't point to anything. So an environment is a sequence of frames. We start in the first frame and look for the variable. If we find a binding, that's it. If not, we go to the next frame and so on until either we find a binding or we run out of frames. In the latter case, it's an error. So if it's a special form, which we tell by looking at the car of the list, at this point it's got to be a list. If it's a special form, then it says here, do special form. That's the big hand wave in this procedure that makes the whole thing fit on a screen. When we look at the real code in just a bit of the Metacircular Evaluator, there's a clause like this for each special form. So it says, is this an if expression? Then eval if exp env. Is this a define expression? Eval definition exp env, and so on. So each special form has its own rules, different from all the other ones. Else, if it's not any of those things, then it's a procedure call. Actually, this is a 61A style don't do any error checking approach. It could be something that's not a valid expression. Maybe you typed in close parenthesis or something. Or maybe you typed in a vector, not a quoted vector, just a vector. You said number sign, open paren, 567, close paren. Which a vector is not a valid expression in Scheme, although some Scheme dialects treat them as self-evaluating. That's not part of the standard. You can't really do it. So really we should say, instead of this else, we should say, is it a list? And if so, treat it as a procedure call, else error, invalid expression. But we don't do any error checking here. So what happens here in this else, these next two lines, are really the crucial thing in the metacircular evaluator, which is how we evaluate a procedure call. So how do we evaluate a procedure call? The first step, before we do anything else, is we evaluate all the sub-expressions. So right here, we're evaluating the first sub-expression, and that's the one that's going to tell us what procedure we're calling, right? Now, more than half the time, that expression is just going to be a symbol, which is the name of a procedure that we defined earlier. Either it's a built-in primitive procedure or you defined it earlier on. So evaluating the car of X will boil down to looking up a symbol, which will turn out to have a value probably in the global frame. But sometimes what's in here is a lambda expression, or maybe it's a call to a procedure that you defined earlier whose value is a procedure, whose return value is a procedure. But one way or another, the value of this thing had better be a procedure. And here is where we're evaluating all the argument expressions. Okay, so cdr exp is a list of all the argument expressions. And this map is going to turn that into a list of argument values. I don't mean turn into as in mutate. I just mean create a list of values corresponding to that list of expressions. And how do we do that? We evaluate each sub-expression in the current environment env. So we can't just say map eval cdr exp the way we could in the scheme 1 interpreter, because eval now takes two arguments. Map wants a function of one argument, namely the sub-expression e. And so we have to say lambda of sub-expression, evaluate that sub-expression in the current environment. Okay? Having done that, we've now evaluated everything. Now we can call apply. And it's apply's job to call the function on those arguments. So this map here, this one, is what tells us that scheme uses applicative order. Right? Because we evaluated the expressions before going to apply. Apply takes a procedure and a list of argument values as its two arguments. So in the world of apply, and this is important to understand, there are no expressions. So this thing that says proc, this isn't an expression whose value is a procedure. It's not, for example, a lambda expression. It's a procedure, which is its own data type. And a procedure isn't something you can type in to scheme. You can't have a procedure as an expression. Procedures are the values of some expressions. And then args is a list of the actual argument values, whatever they are. So these aren't expressions either. These things are, whatever they are, numbers or lists or who knows what. But they're values. So there's no evaluation of proc or args. They've already been evaluated. So apply doesn't know about the notation of scheme at all. All it knows about is the semantics of what it means to call a function with arguments. Well, what does it mean? There are two possibilities. So any procedure that we have is either a primitive procedure or what the book calls a compound procedure, which is one that we created with lambda. Primitive is the ones that are built in. Compound is the ones that were built with lambda. If it's primitive, and this is one of the cheats here, we call it by magic. What that really means is that in a real scheme system, a primitive will have been translated into machine language, into the, ones and zeros stuff that computers actually know how to carry out. So what we're doing is calling that little chunk of machine language code is the way we really handle primitives. How did I get up there? Oops. Ah. Wait. Let's try this again. Okay. Otherwise, oops, there we go. If it's a compound procedure, one that came from a lambda expression, one of those things with two bubbles, then how do we evaluate it? So as always, you have to read this from the inside out when you have a composition of functions like this. So before we look at eval, we're going to look at these inner expressions. And one of them is pull the procedure body out of the procedures. That's one of the things in the left bubble, is the procedure body. And that's a scheme expression. And so that's the way in which expressions sneak into apply. We're not giving it expressions as arguments, but inside a procedure, if it's a procedure created with lambda, there's a procedure body, which is an expression, or actually a sequence of expressions, really. So this should say eval sequence, but this is the short version. The second argument to eval is this thing called extend environment. So we're creating a new environment. That's what procedure calls do. And the way, how do you make a new environment? Remember back a month ago? You take the formal parameters, which come from the left bubble of the procedure, and you take the actual arguments which were given to apply as an argument, and you pair them up. So if we have 3 formal parameters, we should have 3 actual arguments, and we make bindings for each of those, and that's a new frame. And then we use that frame to extend an environment. What environment do we extend? Okay, so here's another important little detail. This does not say env. In fact, apply doesn't know anything about a current environment. What apply knows about is the right bubble of the procedure. Inside of proc-env is a selector. Proc-env and formals and body are 3 selectors for the abstract data type procedure. So now we're pulling out the environment from the right bubble and saying that's the one we're going to extend. So the procedure tells us the environment in which it was created, and that's the one we extend. What's the name for that? That choice of environment? Yeah. Lexical scoping, yeah. What's the alternative? Dynamic scoping, and what does that mean? What's dynamic scope mean? Yeah. Yeah, you extend the environment in which the procedure is called. So if we wanted to do dynamic scope, apply would take another argument, which is env, the current environment. And this would say extend environment, formals proc, args, env. That would be dynamic scope. Lexical scope, the procedure tells us which environment to extend, namely the one in which it was created. Okay? So what I'd like you to see is that I'm telling you again in a different form what you learned a month ago about the environment model. You know, we had pictures on the board with bubbles and boxes and arrows all over the place. This is an implementation of that. That's exactly what it is. So I hope that having seen the environment model will help you understand the metacircular evaluator, and also, conversely, seeing the evaluator will pin down for you maybe how the environment model actually works. I would like you to remark upon the tininess of this code. Now, in saying that, I'm cheating a little bit because I haven't really handled the special forms. Okay? And each special form is, you know, half a screen full of code. So by the time we're finished, it's 6 or 7 screenfuls instead of just 1. And I haven't shown you how to look up a variable in the environment, although that's pretty straightforward. If you know that an environment is a list of frames, then it's pretty simple for you to write lookup in environment, supposing that you have lookup in frame as a helper. But that's basically it. Oh, I'm sorry. I'm also cheating a little bit because I didn't show you read. Read is actually, hang on a sec, read is actually a little messy and ugly because it's dealing with individual characters that you typed. It says, oh, look, this character is an open parenthesis, so I have to do blah, blah, blah. This character is a space, etc. So it's messy, but it's intellectually trivial. You could write it if you really had to. Yeah? Okay, let me try to restate your question, both so that other people can hear it and to try to clarify it for me, too. When you first learned about the environment model, it was presented to you as being necessary in order to achieve the way we want scheme expressions to mean what they mean. And in particular, once we introduced mutation into the language, which we did with object-oriented programming, it no longer works to say we just substitute values into the body, because the value of a variable might change halfway through the body. So as a consequence of that, and as a consequence of wanting things to be lexically scoped, we had to invent this environment model. And that's true. Now, you're seeing the same environment model presented as a consequence of the way the language is implemented. And both of those things are true. This is an instance of a general point that I'll be coming back to at the end of the semester, which is in everything we do in computer science, there's a whole bunch of levels of abstraction. And at any given level, if you're being an engineer at a particular level, what you do is constrained both by pressure from above you, so sort of the needs of the higher levels of abstraction that they're telling you about, and by pressure from below, namely how your level is implemented. Okay, so what kinds of facilities are available for the implementation of your level? And that's exactly what you're expressing here, that you can actually see it both ways. If you look at the actual history of the way this developed, first there was lambda calculus, which was an entirely theoretical model for use by mathematicians and not as a computer programming language. It was an attempt to rest the foundations of mathematics on the idea of function, sorry, rather than the more usual treatment in which everything is based on set theory. So that was a thing for mathematicians. Then John McCarthy wanted to have a programming language in which to make assertions about programs, among other things, to do artificial intelligence research. And he, came across this lambda calculus that Alonzo Church had invented and said, we can use this as a programming language. So he took the notion of lambda, came from Church's work, and he defined a not very good notation for representing that to a computer. And then the notation kind of got refined. The language hadn't been implemented yet. And then one of his grad students, Steve Russell, said, if we represent programs this way, I can write a really simple interpreter for it in itself. He had started out trying to write a Lisp interpreter in one of the previous languages that existed then, which basically meant Fortran. And everybody was finding that impossibly complicated. And Russell had the idea, let me try writing a Lisp interpreter in Lisp. And he came up with basically this, but a little bit different, because they hadn't yet thought about scoping rules. And so they ended up implementing dynamic scope, which turns out to be the thing that you naturally invent if you don't think about it very hard. And I'll be talking more about scope in a bit, probably Wednesday. And then people started writing programs in this language, and we're having certain problems because of the use of dynamic scope. And so there was a lot of, there's 5 or 6 years worth of research papers on how to solve this problem. And then finally they invented lexical scope, which, footnote, is what Alonzo Church had in mind from the beginning. So if they had read Church's papers more carefully, they would have gotten there directly, but they didn't. So there was this back and forth between what the implementers implemented and what the users needed. So the actual history of it is very complicated. But you don't have to recapitulate that history. You have the benefit of all that earlier work. And so you can see, right from the beginning, what kind of the right answer is to these design questions. I'm not, when I say the right answer, I'm not making a claim about the superiority of Scheme over whatever your favorite language is. I'm just making a claim about the superiority of Scheme over the Lisp of 10 years ago or 20 years ago. So yeah, this is exactly the same thing that you learned before. And it had better be the case that what we implement is what we needed, right? So you can view it as the needs giving rise to the implementation or the implementation giving rise to the behavior, and they're both true. That's an example of what we call a dialectic, where you have two kind of opposite things that determine each other. It's another example of circularity, in a way. Okay, we ready? All right. So I'm telling you about the parts we're leaving out. So we left out do special form. We left out lookup in environment. We left out extend environment, but that's totally straightforward. You could have written that in the first, well, as soon as you learned about lists in the 4th week, you could have written extend environment. And we left out read, and we left out print, which is slightly messy, not quite as messy as read. And most important of all, we left out storage allocation. So when you say map, and inside map there's a cons, how does that cons actually happen? That's something we have not discussed at all. It turns out to be probably the most complicated piece of the whole system. And you will learn about it, I believe, in 61B. But maybe it's 61C. They keep going back and forth on this. I think 61B. Okay. Oops. Oops, where am I? Here. All right. Oh, yeah. Something for you to think about. You can write an evaluator for any language in any other language. Okay? They're all completely equivalent in power in the sense of what can we compute with them. They're not equally equivalent in expressive power, which is how easy is it to say what you mean. But they're all equivalent in terms of what we can compute. So if I were to say, I want my class, my introductory freshman computer programming class, to write an interpreter, and I want it to be easy, you might imagine that the thing to do would be to give you a very powerful implementation language, like, say, Ada, which is a language that has everything under the sun in it, or maybe Java, which is semi-everything in it, as the language that you write the interpreter in, and some really trivial language, like, say, BASIC, language they used to use on 8-bit microcomputers, as the language that we're implementing. So maybe writing a BASIC interpreter in Java would be the easiest possible interpreter assignment. Turns out not to be true. Turns out the easiest interpreter in the world is a scheme interpreter written in Scheme. And that seems paradoxical, because I'm saying, on the one hand, Scheme is the simplest language that there is, and on the other hand, Scheme is the most powerful language that there is to write an interpreter in. And how can it be both the simplest and the most powerful? That's one of the hardest ideas for you to take away. And the reason for you to take it away is not so that you become Scheme fanatics. That's not my goal at all. I'm a Scheme fanatic, but you don't have to be. I would like you to be a simplicity fanatic. Okay? I would like you to understand that just as in mechanical engineering or civil engineering or anything else, the best solution is the simplest solution, not the most complicated one with a lot of bells and whistles. And that turns out to be true in programming languages also. So if you ever find yourself designing anything like a programming language, and most of you are probably not going to be designing general purpose programming languages, but you might well be designing special purpose programming languages, like the language that the user of some game uses to say how to move next. That language might be defined in terms of gestures with a joystick or something, rather than stuff that you type. But it's a language. It's a special purpose programming language. And if you find yourself designing one, make it simple. And the way to make it both simple and powerful is to have powerful ideas in it, like, for example, but not only, Lambda. Okay? So Scheme is a simple language because it has a very uniform syntax. So all those parentheses that everybody complains about when they're first introduced to Lisp, they have an important purpose, which is you don't have to understand anything about the meaning of a program to understand how to divide it up into chunks. The dividing up has been done for you by the parentheses. And the other piece of the another piece of the simplicity is that that notation with all the parentheses is both the notation for programs and the notation for data. That's how we represent lists. Okay? If we had a notation in which programs were full of parentheses and quoted lists were full of square brackets instead, that would make our job harder, because we wouldn't be able to take a computer program and view it as data easily. But as it is, after read has done its work, the program that we see actually isn't full of parentheses. It's full of box and pointer diagram, because that's what read gave us. Read is the thing that translates the characters you type, those parentheses and things, into box and pointer form. And then eval is the thing that takes that structure of boxes and pointers and assigns a meaning to it. And then thirdly, it turns out that having a language in which procedures are first class makes writing an interpreter really easy, especially as we get into the more advanced variant versions of the evaluator. You'll see that. Okay. Oh, yes. Now I have to pull out my glasses so I can read this. I'm going to quote to you a piece of the instructor's manual on the subject of data abstraction in the Evaluator. So it's concerning section 4.1.2, which is about exactly how to represent expressions and environments, yeah, as list structure. So 4.1.2. I should point out to you that this section is boring, as is much of section 4.1.3, and explain why. Writing the selectors, constructors, and predicates that implement a representation is often uninteresting. It's important to say explicitly what you expect to be boring and what you expect to be interesting, so that students don't ascribe their boredom to the wrong aspect of the material and reject the interesting ideas. For example, data abstraction isn't boring, although writing selectors is. So in other words, the idea that you can have an abstract data type, like a procedure, say, where we have these selectors, body, and proc-env, and formals, the fact that we can have such a representation is interesting. The particular writing of, formals equals cater and body equals catator and whatever, that's boring. The details of representing expressions, as given in 4.1.2, and environments in 4.1.3, are mostly boring. But the Evaluator certainly isn't. Okay. I actually think, this is one of the few places where I disagree with Abelson and Sussman, I think they go a little overboard on data abstraction. So in the Evaluator, there are many different abstract data types that are sequences of some particular kind of thing, in the same way that a forest is a sequence of trees. And they do a separate abstract data type, not just for the underlying element types, but for each sequence type. So there's an abstract data type, which is the sequence of cond clauses in a cond expression. So there's a selector, first cond clause, and rest of cond clauses. And the same thing for environments. There's a selector, first frame, and a selector, rest of frames. And all of those things are just car and cutter, because whenever you have a sequence of things, a linear boom, 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 boom sequence, car means the first one, and cutter means all the rest of them. And if it were me, I would have the abstraction for a frame or a cond clause, but I wouldn't have a separate abstract data type for each of these sequence things. So I think they make it more boring than it has to be by doing that. Okay. The next thing on the agenda is really to teach you logo. Because in Project 4, you're going to write a logo interpreter. You're going to start with the Metacircular Evaluator and turn it into an evaluator for a whole different language. But we only have a few minutes, so I'm only barely going to get started doing this. Okay, welcome to Logo. You can play with Logo in the lab. Let me start by showing you the most important thing, which is how to get out of it. You say bye. Okay, so that's how you get out. The prompt is a question mark. That's how you know you're talking to Logo and not Scheme. And in Scheme, every expression returns a value. Every procedure that you write returns a value. In Logo, we distinguish certain procedures that return values from other procedures that don't. And this is true in a lot of different programming languages. Right? If you learned C or C++ or Java or Python or any of those, some procedures that you write return values and others don't. If the language is in the C family, they very confusingly use the name function, both for the ones that return values and for the ones that don't return values. In Logo, the ones that return values are called operations, or more recently, sometimes reporters. The ones that don't return values are called commands. So in Scheme, if I say 3, the answer is 3. In Logo, if I say 3, I get an error message. You don't say what to do with 3. Now, the error message does tell you the value. So I can say sum 2, 3, and I get, you don't say what to do with 5. What it wanted me to say is print sum 2, 3. Because print takes one input, prints it, and returns nothing. And a complete Logo command is something that does not return a value. So if the thing you call at top level does return a value, that's an error. You will have noticed that this looks a little scheme-like in that it's a prefix notation where the procedure comes first, but it doesn't have parentheses around everything. As you'll see when you're writing the evaluator, that makes things a little complicated because you have to know how many inputs every procedure wants. So I can say something like, you can abbreviate print to PR if you want. Some product 2, 3, 4. Okay, so think about what the value that should be printed is. You actually do know the answer. I hope that's the answer you got. But in order for this to work, the Logo evaluator had to know that product takes exactly 2 inputs. Okay? Now, in Scheme, product takes any number, the asterisk for times, takes any number of inputs. And actually, you can do that in Logo too. I could have said print sum product 2, 3, 4, like this, and get 2 plus 3 plus 4, or print sum product 2, 3, 4, and get 24. So you can make it do the same thing Scheme would do with parentheses, and we use them in the same way, namely an entire procedure call inside parentheses. But you don't have to. Every procedure, by default, takes a certain number of arguments. Print takes 1. Sum and product take 2 each, if you don't put parentheses in. A big departure is that I can also say print 2 plus 3, print 2 times 3 plus 4. And notice, by the way, that actual Logo knows the rule that you learned in elementary school about multiplication before addition. The one that you write isn't going to be that smart. It's just going to go left to right. This is a compromise. Right? Infix notation is really problematic because of this question of precedence. How do I know which to do first when I see 2 operators like this? It's not a problem with prefix notation. Prefix notation makes it clear which one you want to do first, namely the inner one. Infix notation doesn't make it clear, and that's why people throw in parentheses sometimes to say, like, print 2 plus 3 times 4, if that's what you mean. You use parentheses for grouping because of the ambiguity of infix operators. So infix operators are ugly, hard to deal with for the computer, not that easy to deal with for human beings, if you can remember back to 3rd grade. But it's what everybody's accustomed to, so we compromise and let you use it. 3 o'clock. Okay, we'll continue this next time.